Hi everyone, welcome to Differentials Part 2. Let's get started with a potentially practical example. Our example here is going to be, let's suppose we need to estimate the fifth root of 33. Now suppose you don't have a calculator, okay? That's the whole point. And we need to know what the fifth root of 33 is. So, what we need to do is find the differential with x equaling 32 and dx equaling 1. Okay, so we need a function. Let's let f of x be the fifth root of x. So, in other words, x to the 1/5. Okay, now let's, I want to remind you that we want to find the differential. So we want to find dy, which would equal, just from our definition from before, the derivative of y with respect to x times the differential dx. So first we need to find the derivative of f of x. So let's write it like that. F prime of x. So we take that derivative, we use the power rule. We got 1/5 x to the 1/5 minus 1, so that's negative 4/5. Okay, that's the derivative. So we have, from our definition, our differential of dy dx times dx, our differential, equals 1/5. We'll make the exponent positive by putting it in the denominator, so x to the 4/5 times dx. Now we know some things about our differential. We're supposing that x equals 32 and dy equals 1. Or dx, excuse me, equals 1. So here we go. We want to find dy when x equals 32 and dx equals 1. So let's substitute in. So we have 1/5, and then we have 32 to the 4/5 times, instead of dx, we're substituting in 1. So now this might look a little bit scary, but it's not too bad. Let's find the fifth root of 32. And then we'll multiply that. Well, we'll raise that to the 4th power. So the exciting part is that you can write 32 as 2 to the 5th. And then when you raise that to the 1/5, you have an exponent to an exponent. So you multiply, so you get 5/5. That just gives you 2. So we got 2 to the 4th. So, and 2 to the 4th is 16. So this whole value, 32 to the 4/5, is really just 16. So we have 1/5 times 16, and then multiplied by 1. So 5 times 16 is 1/80. Okay, now that's what our differential is. So remember, on the last video, we said dy, the differential dy, is approximately the change in y. So let me recall. Dy is approximately the change in y. Okay, so we can find the change in y here. The change in y for our example is f of, remember in the last video is x plus dx minus f of x. Okay, here we know what x is. X is 32 and dx is 1. And then we have minus f of 32. So let's substitute that in to our function. So recall f of x was x to the 1/5. So we have f of, well, this is 33 minus f of 32. Let's substitute that in. So we have the 5th root of 33 minus the 5th root of 32, which we just did the 5th root of 32. That is 2. So this really equals the 5th root of 33 minus 2. Okay, now that, remember, equals delta y. And we just said delta y is approximately dy, our differential. So let's see what we have. Let's put it all together. So in the last slide, we got dy was 1/80. And delta y is this thing. So maybe I'll write it in green over here. So we have dy is approximately delta y. We just found dy to be 1/80. That's approximately the 5th root of 33 minus 2. So remember, we're trying to estimate the 5th root of 32, or the 5th root of 33. So let's get that by itself. So we'll add 2 on both sides. So you got 2 plus 1/80 is approximately the 5th root of 33. Now, if you compute the decimal places of 2 plus 1/80, you get 2.0125, and we're claiming that's approximately the 5th root of 33. Now, if you type in the 5th root of 33, we get that equals, the 5th root of 33 equals 2.01234617, and then it keeps on going. Alright, so the point is that our estimate using these differentials and how they are approximately the change in y, we get that they're fairly related, a pretty good approximation. All the way to 3 decimal places, they're completely correct. So the point of this problem is that we can approximate, we can estimate, and then predict the future. Okay, let's do one more practical example here. So sometimes there's companies, and when they make different things, there's errors in production. The errors are the differentials that we're talking about. So for this example, it says the radius of a sphere is measured to be 10 inches with possible error, so differential, of 0.1 inches. Use differentials to estimate the maximum error in surface area. So again, we have to come up with our constraint equation. Our constraint equation is going to be the surface area equation. So perhaps you forget what the surface area is for a sphere. However, you can just Google it. I will not require you to know the equation for surface area on the exam. So if you Google surface area of a sphere, we have the surface area equals 4 pi r squared. Okay, now what do we need to find? We need to use differentials to estimate the maximum error in the surface area. So we need to find the error in surface area. So we need to find ds. We know a couple values. So we know that well, okay, before we say what we know, let's actually find ds. And then we'll plug in some points. So ds, it's going to be our differential. So ds equals ds with respect to r times dr. So it's the same definition. You can imagine the dr's are canceling. However, there's more happening underneath, so they don't technically cancel. So we need to find ds over dr. So we're going to use our constraint equation. And we're going to do implicit differentiation. And we're going to take with respect to r. So the left-hand side, the derivative. So I'm looking at this equation here. The derivative of s is just 1, and then we have ds dr equals the derivative, the only variables are, we bring down the exponent, so it becomes 8 pi, and then we have r to the first power. So that's what our rate of change is, the rate of change of the surface area with respect to r. So then substituting into this equation, we get ds equals ds over dr, which is 8 pi r, times the differential dr. Now we want to know what ds is when the radius is 10, and when the possible error of the radius is 0.1. So dr equals 0.1. So we're going to substitute that in. So we get 8 pi, instead of r we have 10, and then instead of dr we have 0.1. So our answer is 10 times 0.1 is just 1. So our answer, the possible error, is 8 pi.